Perfect. We are live. Hey everyone, this is Xibei from Dora Hacks. Thank you all for tuning in for today's Dora Dōjō workshop. Today we're very honored to invite Michael to join us to share his knowledge and insights with us through his astronomy research. So Michael is an astronomer, research scientist at SETI Institute and research assistant professor at Rochester Institute of Technology. And the topic for today's workshop is gravitational wave astronomy with a precision pulsar timing array detector. So this is actually the first Dora Dōjō workshop episode on astronomy. As we at Dora Hacks ventured into supporting space tech innovation this year, we see astronomy as foundational in driving our passion for space exploration. So yeah, we're very glad and honored to have Michael join us today to kick off our workshop series on astronomy. And we're so excited to hear Michael's insights on this fascinating topic. I'm pretty sure everyone who's watching this episode will have some great takeaways. Before we kickstart the workshop, just let me quickly give you a brief introduction about who we are and what we've been working on. So for those who don't know Dora Hacks yet, we are a global hackathon organizer and one of the world's most active developer incentive platforms. We love to support innovation in blockchain, quantum computing, space tech, and many more. And we provide a wide range of toolkits to help developers around the world team up and fund their research, ideas, projects via hackathons, grants, bounties, etc. And Dora Dōjō specifically is an open source knowledge community co-built by global hackers focused on cutting edge technologies. So Dora Dōjō regularly organizes and shares sessions in the form of live broadcast, audio, and text, covering a variety of topics such as cryptography, quantum physics, astronomy, and spacecraft system design, etc. Yeah, so that's pretty much about us. One more note for the audience during the workshop, feel free to share any questions you have in the YouTube chat room, and I will make sure to ask Michael your questions at the end. So now, without further ado, let me give a warm welcome to Michael. Welcome, Michael. I'm happy to pass the mic to you. How about you kick it off by giving us a brief introduction about yourself before diving into the workshop content?
Sure. Thank you so much for the lovely introduction, and it's a pleasure to be here for the first of these workshops. So my name is Michael Lamb. I'm currently a research scientist with the SETI Institute. I've been an astronomer for many years now, working as part of this collaboration, which I'm very happy to tell you about, the North American Nanohertz Observatory for Gravitational Waves, or NANOGrav. And I know that's a mouthful. By the end of this talk, you should understand what all of those different parts are. So I've been working with this group for many years, and we, alongside several other groups this past summer, have made really exciting announcements to the world, opening a new window to the universe. So it's my pleasure to bring you all along as we've opened this and started this journey. So I'm glad you're all joining us for that. And in the past, what I've done is I've given talks with a title sort of like this. It's a little bit dry, but it's gravitational wave astronomy with a precision pulsar timing array detector. And that's what you're going to hear today. But really what I should do now in the last couple of months is change the title of my talk to Evidence for a Gravitational Wave Background. That's because we've done some really exciting stuff in the last couple of months. Well, it's taken many years to do this, but we've announced it only a couple of months ago. And what I'm going to do first is start with the evidence, and you won't quite understand what any of this means, but by the end of this talk you will. The evidence that we have takes two forms, and it's a little bit confusing, so I'm going to go through it. The left plot, which again you don't quite understand right now, explains what the sound of the gravitational waves are like, and that it's sounds similar throughout our entire detector. And then the right-hand side, we have evidence that there's a correlation between the components of our detector. And again, you don't quite understand what that means, but we're going to get into that in this talk. And we've had evidence for a long time of the left-hand part, so the first piece of our evidence. And on the right-hand side, that's what many of the groups around the world, NANOGrav included, have recently reported, really opening this window into the gravitational wave universe. And from this evidence, what we realize is that we are really living in a sea of gravitational waves. Um, there have been several detectors on the ground that have been observing gravitational waves for the last many years. These are LIGO, Virgo, and CAGRA. Uh, and what they have done is they have detected what we call transient gravitational waves. That is something that goes bump in the night and produces a flash of gravitational waves, and then we don't really see much else. And there's another flash of gravitational waves, and then we don't see much else. That's what's been seen so far. And from all of our experiments in this pulsar timing array community, we really see that gravitational waves are permeating throughout space, that space-time is changing in a certain way that I'll get into in a couple of slides, and that really it's pervasive throughout the universe. And so it's an incredibly exciting time to be in astronomy in general, and specifically in gravitational wave astronomy, because we're actually able to make these observations at this point in time. So I mentioned that I'm part of the North American Nanohertz Observatory for Gravitational Waves, or NANOGrav. And the first part of that is very easy. North America, we are primarily based in North America, although we have members around the world. We use North American telescopes, and the 4 of those that we used are seen here. Starting at the bottom right, we have the Arecibo Observatory, which unfortunately collapsed several years ago. That was a 300-meter telescope, and that provided us a lot of sensitivity in our observations. We've also used the 100-meter telescope in Green Bank, West Virginia, which is the largest fully steerable object on the planet, so it can rotate around and bend up and down. And you can see some students of mine and other students from the university I was working at last year, all the way at the top of the very arm of the Green Bank telescope. We, in the last several years, have been using the Very Large Array in New Mexico, and as of very recently, I've been using this new telescope called CHIME, which is in British Columbia. And so these radio telescopes form part of our gravitational wave detector. They are observing the other objects in the galaxy that make up the rest of our detector, which I'll get into in a little bit. And of course, there are many, many, many people, nearly 200 individuals, not including students, undergraduate students, primarily based in North America. So it's a very big effort, and it took a lot of work in order to make this happen. All right, so that's the North America part. Now I want to talk about the gravitational waves part. And for thousands of years, astronomy looks something sort of like this picture. This is a picture by a famous astrophotographer who's taken up a camera and has pointed up at the Milky Way. So you're seeing our galaxy. It's a little bit better than what you would see with just your eyes, but if your eyes could sort of hold open and collect all of the photons coming at you, that's what the image of the Milky Way would look like, and the sky overall. And you can see the band of the Milky Way, so the galaxy we live in, it's brighter in certain patches. There are other parts which are dark. And that's the view that astronomers have had for thousands of years. And about 100 years ago, we opened up the next window to the universe with the radio sky. Engineers and then astronomers started building radio detectors and then radio telescopes, and then looked at what the sky appeared to be in radio wavelengths. And when you do that and you make a map of the sky, you see something that looks like this. You see that it's very different from what I showed before. There are these bubbles and wispy structures, there are these bright objects, and there's still all of these dots. And very importantly in this image, each one of these dots is not a star like I showed in the last image. Each one of these dots is a quasar, which is a supermassive black hole, billions of light years away. And by collecting more information at other wavelengths of light, we're able to see a different universe entirely. The physics of the universe, the underlying components that make it up, look entirely different. And if I were to then build telescopes across the electromagnetic spectrum, which is what astronomers have done over the last 100 years, we see that there's different radio telescopes up at top going into the infrared. Down near the bottom, there's optical, and then X-rays, and then gamma rays at the very, very high energy range. We see that the universe looks completely different. This is just a cutout of our Milky Way galaxy, but even from there, you can tell that there's lots of differences. And so if we only built one kind of telescope or another kind of telescopes, we would only have a limited amount of information about what the universe would look like. And so astronomers have tried to build telescopes across this electromagnetic spectrum to get as much information as possible to understand physically what's going on in our universe to the best of our ability. Well, now in recent years, we've entered an era of what we call multi-messenger astronomy. That is, not only are there electromagnetic waves, there are other types of messengers that we can observe. And one of the most prominent messengers that we have in the recent years are gravitational waves. And this is a schematic view of the gravitational wave spectrum. So on the bottom axis, you can see that there's frequency of how fast these waves are oscillating, going to the right, or then the length of the gravitational waves, the period, going to the left. And then there's some measure of the strength of gravitational waves in the y-axis, and I'm going to get into that in the next couple of slides. So in 2015 and 2016, ground-based interferometers became the first gravitational wave detectors to view the sky. Those are those transient gravitational waves that I mentioned earlier. That's LIGO, Virgo, and now COGRA. And those are on the very high frequency gravitational wave end of the spectrum. Things that are spinning around, orbiting hundreds or thousands of times a second, that's what those types of detectors are going to be observing. Pulsar timing arrays have now announced evidence for gravitational waves at the low frequency range. And you can see down here that we are in the nanohertz regime. And nanohertz is a weird unit. That's 10 to the minus 9 hertz. That means that that's equivalent to things orbiting around with a 31-year period. And so pulsar timing arrays are sensitive not to things spinning hundreds of times per second, but things spinning around with periods of weeks to months to years to decades. And so that's the part of the spectrum that we are able to observe. And that's very different from the part of the spectrum that the ground-based interferometers are able to observe. So there's different physics, different physical objects in the universe that we're able to take a look at and observe. So we are the North American Nanohertz Observatory. So we are observing a very, very long period, very low frequency gravitational waves. And we are the second such one of these experiments that have opened the window to the gravitational wave spectrum. Okay, so what are gravitational waves? Gravitational waves are commonly referred to as ripples in space-time, and that's kind of how I like to think about them. They're generated from objects that are, for example, spinning but don't have to be spinning, or orbiting around each other, things that are spinning with bumps on them. Lots of different objects are known to emit gravitational waves. The effect of gravitational waves very far away from those sources is such that if a gravitational wave is passing straight through the screen right at you right now, and there were a ring of particles oriented in a circle, then as time passed over to the right, the ring of particles would stretch in one direction and compress in the other, come back to a circle, and then compress and stretch in the other direction and come back. So it would do this elegant sort of dance this way. And gravitational waves can also have a polarization such that particles may also squash and stretch on a 45-degree angle. But the net effect is such that if you have a ring of particles, space itself is actually changing distances. The distance between those objects is changing ever so slightly, here very exaggerated. And we describe the strength of gravitational waves as the fractional change, the little delta L, how much it's changing, divided by the length L of the particles overall. And that strain h, which is delta L over L, that's the fractional change in distance. That's what we call the strain. And that's the amplitude of gravitational waves. Here it's enormously exaggerated to something like a strain of 0.1. LIGO first announced a detection of gravitational waves where the strain amplitude was 10 to the minus 21. So that is a fractional change in distance of 10 to the minus 21, 1 part in 10 to the 21. For NANOGrav and other collaborations, we're announcing strain amplitudes of 10 to the minus 15. That's 1,000,000 times larger. But that doesn't necessarily mean that ours was an easier experiment. It's just that the strength of those gravitational waves at those frequencies is much larger. But still very tiny, 1 part in 10 to the 15. It's a very tiny number. So that's the effect of gravitational waves on space-time. It's actually changing the distances between you and me right now. And so we need to build a very sensitive detector in order to do this. And what we have used in my community are objects called neutron stars. And I'm not going to give you an entire lecture on how stars live through their entire lives. I'll say very briefly that most stars in the galaxy follow the left-hand path where they become a sun-like star. They live for many billions of years, they grow old, and then they puff out their outer layers, and they end up with a very compact object at its core called a white dwarf. Very massive stars, many, many more times the mass of our sun, will end up taking the right-hand path, and at the end of their lives undergo a supernova explosion. And in that explosion, one of two objects can be left at the very center. The most massive stars will leave behind a black hole, and the only very massive stars will leave behind a neutron star. And it's these neutron stars which are incredibly interesting objects in their own right and can be used as tools to find gravitational waves. These neutron stars typically have about 1 to 2 times the mass of the sun, but you compress them into a ball with a radius of about 12 kilometers. So take the entire mass of the sun, and the sun is about 100 times the radius of the Earth, and you compress into a ball about 12 kilometers. So here I show what that size looks like. I knew that was going to happen, embarrassingly. Hopefully you can all hear me still. Here you can see what that ball looks like over New York City. And so you take the entire mass of the sun compressed over New York City. You get one of the densest objects, really the densest astrophysical objects in the universe. They have a density that's the same on average, and actually more dense in the center, than that of the nucleus of an atom. And so they're incredibly interesting objects because it's the only place in the universe we can go to look at what matter does at those extreme densities. Not only are they extremely dense, they're actually very quickly rotating. The objects maintain the angular momentum from the original star. And so you take a big star, and then if you are conserving the angular momentum into this really tiny ball, they spin very rapidly. Most of these objects have spin periods between a millisecond and up to about 10 seconds. And for my collaboration, we observed the very fastest of these spinning objects. So the one spinning with millisecond periods, that is, they're spinning hundreds of times a second. So you're taking this very massive, very dense, compact object, and you're spinning it hundreds of times a second. On top of that, they have a radio beam, or most of them have a radio beam that is offset from its rotation axis. And so they act very much like a lighthouse does, where if I'm using my pen here and you have the beam is offset from the rotation axis, like I'm showing in the diagram, and I'm spinning it, every time the beam passes your line of sight, we see this radio emission. And so what that looks like are a set of pulses, one pulse every time the beam passes our line of sight. And the first set of pulses ever detected are shown on the right-hand side. by then graduate student Jocelyn Bell Burnell. You can see that the dips here correspond to the pulses being observed from this first object, which became known as a pulsar. So a pulsar is not a pulsating object. It's not getting bigger or smaller. It's just acting like a cosmic lighthouse. And as it does so, we see these pulses, and we can use these pulses because of this very, very, very fast and stable rotation. We can use these objects as very accurate and precise astrophysical clocks. And from that, when you put a clock into space, you can start to do really cool fundamental tests of physics. One of the things that we have done is use those to build a detector of gravitational waves, but you can do lots of other cool things, which unfortunately I can't talk about in the time that I have here. But I want to impress upon everybody just how awesome these objects are, how precise these objects are. And so I've taken one of our best objects in our data set, but certainly all of them are very, very, very similar in precision to this object. And I have measured, my collaboration more correctly has measured, in roughly the middle of our data set. So that's July 13th, 2012. That's where that time comes from. What is the spin period? How long does it take for this pulsar to rotate around? And the answer is one of the most precise measurements you will ever see. It's 2.9 and then all these digits, milliseconds, plus or minus this 2. And this 2 here is the error bar on that 7. Okay, so it's one of the most precise measurements that you're ever going to be able to make. We also know that because these pulsars have these radio beams and they're emitting this light, as they spin around, they're losing energy to this light. And that loss of energy slows them down just ever so slightly over time. And I'm able to measure that slowdown as well. And so I know that the last digit, the 7, changes by 1 and increases by 1 every 713 seconds. That's about once every 12 minutes or so. So every 12 minutes, that goes up by 1 or so. It means that this digit over here, this 0, changes by 1 every 226 years. So I know the spin period of this pulsar, and it's slowed down extremely precisely. And that means that with that level of precision, I'm able to count exactly when pulses arrive at my telescope, each and every individual pulse. So I know that between this time in the middle of our data set, July 13th, 2012, and the start of this talk, September 13th at 13 UTC, the pulsar has completed exactly this many rotations around, 119 billion rotations, and you can see the exact number there, and I can actually tell you that it's halfway through that next rotation as it was going through. So they're extremely precise clocks that nature has given us. A little bit more fun with this pulsar, just very quickly, is that this one itself, and one of the reasons why I pick it, is one of the most precisely measured circles in the universe. And so it has the smallest eccentricity of any known binary. That is, how away from a circle, how oval is it? How elliptical, rather, is it in shape? And it's got an extremely small eccentricity. And so it's very, very tiny. And then when you work through all of the math and you get to the bottom line, I know that the difference between the long edge of that ellipse and the short edge of that ellipse, the semi-major and the semi-minor axis, is 3.5 microns. Extremely tiny. It's almost exactly orbiting around its binary companion in a nearly circular orbit. But I know from our measurements that it's not exactly circular, and I'm able to measure that with that level of precision. So that's very cool. We need this level of precision because the effects of gravitational waves, as I mentioned before, are extremely tiny. Just doing some hand wavy math, we can say that over the lifetime of our experiment, so say it's a decades long experiment, light travels for many tens of or several tens of light years. And given the typical strain for our expected sources, this is the strain amplitude at our frequency range. And I'm not going to justify that right now, but I did mention before that what we have announced evidence of was around 10 to the minus 15, so right in that range. The change in length over these light years is something like 10 to 100 meters. And it's a little bit of a subtle point, but that's just the duration over the lifetime of our experiment. These neutron stars are thousands of light years away from us, deep in the galaxy. I'm going to show a map of that later on. So they're thousands of light years away, and we need to be able to measure the changes in space-time, how much space is compressed or stretched by something like the size of a football field. And that's an incredibly tiny amount. Converting that into a time change, we need to be able to measure when pulses arrive at our telescope to much better than about 1 microsecond, hundreds of nanoseconds. And so it's an incredibly tiny effect, but if I can measure when pulses arrive and say this pulse arrives and I can measure it to within about 100 nanoseconds, then I should be able to measure the effects of gravitational waves. All right, so how do we do that? We have some neutron star, some pulsar spinning off in space, and that pulsar will be sending pulses to us, which we can time. But our telescopes here on the Earth are not floating in space. They're on the Earth. The Earth is spinning around on its axis, and then it's also orbiting around the sun. And so where the telescope is in the solar system is changing from moment to moment. And we need to be able to take that into account because it takes light about 8 1/3 minutes, about 500 seconds. That's the light travel time between the sun and the Earth. So from one side of the orbit to the other side of the orbit of the Earth, that's 1,000 seconds. And if I need to be able to measure precisely when pulses arrive to within 100 nanoseconds, I need to know exactly where the telescope is in our solar system. On top of that, most of our pulsars happen to be in binaries. So they're going around in an orbit of their own. And each pulsar is in its own binary that we cannot go and measure. So there's nothing we can do except from our data, try to measure what those binary motions are looking like. The pulsar system and the Earth-Sun system are traveling through the galaxy, and so they're moving with respect to one another, and that's going to change the distance between us and the pulsar as well. We have to take that into account when we measure the times of arrivals of these pulses. To make the matter even more complicated, space is not empty. The space between all the stars is filled with a medium called the interstellar medium, gas and dust. And just like when you shine light, optical light through a prism and it splits up into the rainbow, when you send radio light through this interstellar medium, that splits up between red and blue. And so over here on the left, it's easy to count exactly which pulse number I'm on, but on the right-hand side, it's a lot harder. And so we need to be able to correct for that effect. And then on top of all of that, the tiny effects of gravitational waves are passing through our detector. And so from all of these measurements, we need to be able to pull out gravitational waves. And that's why we can't do it with just one pulsar. We actually need many pulsars, because with just one pulsar, we would never be able to confidently say, yes, we've seen gravitational waves, and it's not some other effect that's changing when pulses arrive at our telescope. So what we do in my collaboration and other collaborations around the world is use the method of pulsar timing. And that is to build a model that very accurately predicts when pulses should arrive at our telescope. And so you can see on the top plot, if pulses are being emitted and arriving regularly at our telescope, we can model that with a black line. In the middle panel, if I have data where the pulses are arriving with a different cadence, you see that that model is no longer good. And so we have to generate a better model, which I show in the bottom. That's a better model. It's actually accurately fitting the data that we have. That model now describes all of the motions of the pulsar and the Earth system. And we need to do that for each one of our lines of sight. And in the NANOGrav collaboration, we're observing almost 80 different pulsars at this moment in time. For the data set I'm going to be talking about, we use 68 of these pulsars. So those are ones where we've been observing for at least several years to include into our data set. So our detector has 68 different arms, each Earth pulsar arm spread throughout the galaxy. And that's what we needed to do to make these observations. If I take my data in gray, simulated in gray here, minus my model, I come up with what are generically called residuals, and residuals are a measure of the goodness of the fit. Data minus model is the residual, and if my model exactly matches my data, then my residual should be 0. And so our models are pretty good. You can see for one of our pulsars here, I would focus more on the bottom panel where we've averaged our times of arrivals, our TOAs, that we are getting within our model is matching our data along the 0 line well within 1 microsecond. You can see here that the range on the y-axis is between plus and minus 1.5 microseconds, and that all of the points are well within that range. So for this pulsar, we are seeing sub-microsecond timing, and that is exactly what's needed to look for the signatures of gravitational waves. That somewhere left over in those residuals are going to be these different signatures. Now, what are those signatures going to look like? They're going to look like something like the set here, and I'm not going to focus on the bottom one just now. I'm going to start with the middle one, actually, the continuous wave. If there was, for example, one binary source of gravitational waves very far into the universe, as they orbit around, they're going to emit gravitational waves, which when they hit our detector, are going to cause space to compress and stretch and compress and stretch periodically in a sinusoidal fashion. And so in our residuals, we should see one sine wave. That's not actually what we've announced evidence for, and that we expect to be coming in the next couple of years. What we've announced evidence for is in the top, which is what's called the stochastic background. That is not that there's just one binary system that we've observed. We've actually observed the collections of hundreds of thousands or millions of binaries spread throughout the universe. And each one of those binaries is sending this kind of sine wave pattern at us. But they're sending sine wave patterns at different amplitudes and at different frequencies. And when you collect all of that together, the signal that we measure is not a deterministic one, but it's a stochastic run. It's this random process. And it looks kind of like a random walk, kind of like the red line that you see here. And that's what we needed to pull out of our data. And for each of our different pulsars, that random walk will look a little bit different, but the characteristics of that random walk will be the same. So the amplitude of the random walk and kind of how smooth the random walk is should be the same amongst all of our pulsars if it's from gravitational waves. And in order to really confidently say on top of that, that yes, we are seeing the stochastic background and not some other source that's common to all pulsars individually, kind of in isolation, we need to correlate the signatures from all of our different pulsars. So we look at the residuals from all of our different pulsars and we correlate them, and we correlate them in a way that we know comes out of predictions from general relativity, and it produces this curve here, which is known as the Hellings and Downs curve. And what this tells us is, for example, if we have 10 pulsars in exactly the same direction in the sky, all of them are in the same line of sight. They don't know anything about each other because they're all at different distances. But if space expands a little bit along that line of sight, then all of the pulses should arrive late. And if space compresses, then all of the pulses from all of those individual pulsars should arrive early. So they're behaving in a correlated way. And if instead of being 0 degrees separated on the sky, they're 10 degrees or 20 degrees or 30 degrees separated, then there's going to be this correlation pattern. We can see that a little better in this graphic here on the left, where if I have 3 pulsars somewhere on the sky and I correlate them, so let's say I take the circle and the star, they are just over 20 degrees separated on the sky, they would produce a plot here, and this is the expected correlation that we would see. This is due to general relativity, and we can even use this to, for example, test alternate theories of gravity beyond general relativity if this shape, for example, is a little bit different from what we expect. So that's what we're doing. We're using pulsar timing, and we're observing an entire array of pulsars to build a pulsar timing array detector. And here's a snapshot of this lovely movie made by Onyx Lee, where we can see on a schematic map of our galaxy where all of our pulsars lie. And so we really do have a galactic scale detector, a detector that spans a good fraction of the size of our galaxy. That detector is made up of 68 at this moment of these very accurately and precisely spinning pulsars and our radio telescopes here on the Earth. And so it is one of the largest detectors that one can possibly build. And that's what we've done for many, many, many years. Our data set has grown tremendously over many years. The results that I'm talking about today and we've announced several months ago are from NANOGrav's 15-year data set, its fifth data release as we've gone along this entire lengthy process. And as we've gone along, we've observed many, many, many more pulsars. So on the y-axis, you see time, and each column here of points is an observation of one pulsar. So you can see all of our different 68 pulsars all in a row here. The colors represent different radio frequencies that we're observing with. And so as time has gone on, we've added more pulsars to our array. We've observed for longer, which means we are sensitive to gravitational waves with a longer period. And what's not really shown here is that our instrumentation on our radio telescopes have improved tremendously, that the radio frequencies we're observing with have just grown by an enormous amount. And so that's made our data set the most sensitive one in the world at this time for this kind of experiment. We're just able to correlate lots of different pulsars against one another to look for gravitational waves. And so that's what we've done. This falls into the broader picture of multi-messenger science, where we combine in the future gravitational wave observations with electromagnetic observations. And I've already mentioned that there's lots of different kinds of electromagnetic observations. And the main picture that we were hoping to be able to tell you about, and that gives a little bit of a hint to where we are right now, is to look at this picture of how supermassive black hole binaries merge throughout the universe. LIGO, Virgo, and Kagra are these ground-based interferometers. They have been looking at stellar mass objects, stellar mass black holes, stellar mass neutron stars, and the mergers of those. So when two of them are in a binary and they merge and they emit gravitational waves. For us, we're trying to observe supermassive black holes, so objects with 1 million to 10 billion times the mass of the sun. And every regular galaxy in the universe has a supermassive black hole at its center. Our Milky Way has a lower mass supermassive black hole. It is only 4 million times the mass of our sun. And we are really sensitive in pulsar timing array observations to those on the very high mass end, 1 billion and 10 billion times the mass of the sun, maybe a little bit lower than that. And we also know from electromagnetic observations we've seen for centuries that galaxies merge. And so as they merge, and there's supermassive black holes at the centers of those merging galaxies, they've come together. And when they get very, very close, they start to emit gravitational waves. And so our observations slot into this bigger picture of how galaxies merge and evolve and grow over the entire span of the length of the universe. So that's what we were hoping to do in our observations. Okay, so now let me go back and tell you, let's go all the way back to the beginning and let's talk about the evidence. The evidence is as follows. What you see here is a plot of the strength of gravitational waves, if you will. Really, it's the amount, the deviations in our times of arrival. That's on the y-axis. So how much, it's a measure of how much the times of arrivals are changing as a function of the gravitational wave frequency, which is on the x-axis. And you can see we're at -9, so that would be 10 to the -9 hertz. That's 1 nanohertz. So we're just above 1 nanohertz. We see a common process, that is, in all of our pulsars, there is a random walk-looking thing that all behaves sort of similarly. It all has a power spectrum. That's what we're seeing here. That's what we call red. So there's more power on the low frequency side than the high frequency side. That comes out of signal processing language. And the red part of that comes out of color. So the color red has more power at long wavelengths at lower frequencies than blue does. And what we can see is that there's a common process in our data that somewhat follows a power law. And the black dashed line is the expectation for what supermassive black hole binaries are supposed to be doing throughout the universe. And you can see that our best fit to each of these individual frequency bins is given by the blue line here. Regardless, the Bayes factor, which is a measure of how much I would bet on how strong this process is, this common process amongst all of our pulsars. How does it sound in all of our pulsars? That is a Bayes factor of 10 to the 12. So that is, it's not quite the betting odds, but I'm going to say that it's sort of like the betting odds. How much would you bet? And you would bet 10 to the 12 to 1 that this is in our data. And that's not actually that surprising. In our previous data release, and in fact the data releases of other collaborations around the world, there was not 10 to the 12, but there was very strong evidence for this common process. So this has been known. This first piece of evidence has been known for the last few years now. That is that the pulsars are behaving in a way, they're deviating from their perfect rotations in a way that's consistent with gravitational waves. The first piece of evidence there. But what we really needed was the smoking gun of this Helling-Downs curve. And that's what we are announcing evidence of. That here is the measurements from just the NANOGrav collaboration, and other collaborations around the world, as I've mentioned, have announced similar evidence. For us, we have Bayes factors of 200 to 1,000, depending on what kind of analysis that you do. And we've gone even further, and instead of using this Bayes factor methodology, we've really dug in deep and tried to come up with p-values, which are a measure against the null hypothesis, against whether or not we would have observed this by random chance if there was no gravitational waves. And depending on the kind of test we do, we get p-values which are very, very small. Very typically in the literature, in lots of literature, you try to look for p-values which are less than 0.05. If you convert that into sigmas, if you think about that as if it were Gaussian, it's not exactly Gaussian, it's something like 3 to 4 sigma. So it's very, very, very strong evidence. We as a community have decided that it's not enough evidence to call it a detection, which is why I'm trying to be very careful with my phrasing. We're taking that from the particle physics community, which kind of uses 5 sigma as this threshold. But I would still nonetheless argue that there's enormous evidence for these gravitational waves. We have this common process that has an incredibly statistically significant value, and now a very strong measure of this Helling-Downs curve. So there's 2 pieces of this evidence that we have, and so we think that that these are our observations. So the evidence for our gravitational wave announcement is sort of twofold. And what I'm showing here is a plot of the sound of gravitational waves, as I've made an analogy. That is, how do the gravitational waves appear in our data set? And we see common to all of our 68 pulsars this sort of a signature. So on the y-axis, you're seeing the deviations in the arrival times, so how far away from a perfect clock we are, as a function of the gravitational wave frequency on the x-axis. And remember that 10 to the minus 9, so minus 9 here would be 1 nanohertz, so we're in the nanohertz regime. And these are the measurements that we have. Everything is consistent with a power law. That power law that's predicted from one model of how gravitational waves from supermassive black hole binaries exist. One of those models is shown with just the dashed black line. So you can see that all of our measurements are consistent with that. I'm showing a number here that's called the Bayes factor, and that's sort of like the odds at which I would bet on this this observation being the case. It's not quite that, but it's close enough for the purposes here. And so it's sort of like saying you would take a 10 to the 12 to 1 bet that there is a common process, that all of our pulsars are behaving with a random walk signature with the same amplitude and the same kind of smoothness to that random walk. And this is not new. We've seen this in our previous data sets, and other collaborations around the world have seen the evidence for a common process amongst all of our pulsars in their data sets, with lower significance previously, but still very, very strong significance. What's new here is that, and which prompted us to say that we have evidence for gravitational waves, is evidence of this Hellings and Downs curve. That is the correlations between all of these different pulsars. And so we have a base factors there, depending on the analyses we do, between 200 and 1,000. And we really dug into that a little bit deeper and did more proper null hypothesis testing. And so a very common what's called p-value in the literature is to say that something is below, say, p of 0.05, then there is an effect that does exist, and if it's not, then it doesn't, or there's evidence for it. And we're seeing very, very, very small p-values. And if you like to think about that in terms of sigmas, that's something like a 3 to 4 sigma effect. And so we have very compelling evidence. We have very strong signature of a common process in all of our pulsars, and we have what I would call moderate evidence for them to be correlated amongst all of our pulsars. So it's these two pieces of evidence that lead us to say that we are observing the gravitational wave background. Okay, so what does that mean astrophysically if we have this background? We unfortunately are not able to say with certainty what the sources of gravitational waves are at this time. What we've done instead in my collaboration is assumed that if all of the gravitational waves come from supermassive black hole binaries, which is a pretty good assumption, but let's assume that, or I should say most to all of the gravitational waves are coming from supermassive black hole binaries, then we're painting a picture that's shown by the gray contours over here. And we've looked in depth at all different models, theoretical models about how galaxies should merge through the universe, how supermassive black hole binaries should grow, what is the interaction between those two. And we're painting a picture that, because we've made these observations now, that the universe favors models that, the universe favors models where supermassive black hole binaries either are more abundant or more massive, or both, than models where they're not. And also that they're interacting with their environments. That is, that the binaries are not they're not orbiting in isolation, but that there's gas and dust or stars or other things in their local areas that drive them to merge faster than otherwise. We're not yet able to tell the two different models apart with certainty, but as time goes on and we collect more data, those contours that we have here should shrink and shrink and shrink, and then we'll be able to say with better precision which models of how galaxies evolve over cosmic time, and how those supermassive black hole binaries evolve over time, which one of those are preferred. So it really points us to collecting, points us towards the future where we should be collecting more and more data. And that really, this is the, as my postdoctoral advisor, Maura McLaughlin, said, the end of the beginning, that we have come to this point in the process where we have shown evidence for gravitational waves, but now we want to actually do gravitational wave astrophysics with that. And that will just take more time. The other possibility that's very exciting is that the gravitational waves come from a wide range of what we're calling new physics. That is, physics beyond the standard model of particle physics, where if it were observed, would sort of change the way that we view our complete understanding of the universe. Many of these models of new physics come from sources that are cosmological in nature. That is, they deal with the universe as a whole, or they deal with the very, very early moments in the universe, close to the Big Bang or close to inflation. And what we were able to do is rule out some models, some theoretical models of new physics, but not all of them. And so in reality, what's probably happening is that the gravitational wave signature that we're observing is a mix of gravitational waves from supermassive black hole binaries and gravitational waves from some type of new physics. And so as time goes on and we get more and more sensitive and we collect more and more data, we'll hopefully be able to disentangle the components and be able to say what parts come from these exciting new areas of physics, what parts come from supermassive black hole binaries. One way that we'll be able to do that is by actually mapping what the sky looks like in low frequency gravitational waves. And so what I'm showing here is from a recently accepted paper by the NANOGrav collaboration, where we've not yet been able to map the gravitational wave universe. But we're able to put upper limits. So each one of these maps in the sky is showing the upper limits for how strong the gravitational waves are in one direction or the other direction. And if the sources of gravitational waves are cosmological in nature, then the gravitational wave universe should be completely uniform. And if there's coming from supermassive black hole binaries, well, if there's more galaxies in one direction of the sky close to us than another direction of the sky, then, or there's a more massive binary close to us in one direction than another direction, then the universe will start to look patchy. And so we're seeing here upper limits, but these upper limits are getting very close to the expected level of what we call anisotropy, the deviations away from perfectly smooth. So it's an incredibly exciting time. We're approaching the regime in which we can provide you with a map of what the low frequency gravitational wave universe looks like. And I want to end on my last two slides by pointing to future facilities that will help make this happen. One facility that NANOGrav is really pushing for and trying to be a part of with other collaborators around the country is this telescope concept called the Deep Synoptic Array, the DSA 2000. And the idea here is that it will be made of 2,000 of these dishes. Each one of these dishes is 5 meters across, so they're not really small dishes. And when you add up all 2,000 of these dishes in the collecting area provided by those, you get an equivalent area, an equivalent sensitivity to the Arecibo Observatory, which is the telescope that collapsed in Puerto Rico that was 305 meters across. Importantly for NANOGrav science, this will have state-of-the-art instrumentation, so we'll be able to observe a wide range of radio frequencies. It will sit, hopefully, if all goes well, in some region of the country which has a very low radio interference environment. And so here is one proposed site, which is in this valley. It's a little bit hard to see, but here's all 2,000 dishes schematically shown, being shielded by this unpopulated valley. And on top of that, NANOGrav would get a large fraction of the time available on this telescope. And that will allow us to observe many, many, many more pulsars. The more pulsars we have, the more sensitive our detector is to gravitational waves. So I'm really excited that all of you are joining us in this future-looking era towards opening up the low-frequency gravitational wave universe and joining us for the really exciting science that will come in the many decades. So thank you very much.
Awesome.
Right, hopefully
Thank you so
that
much,
one did
Michael.
work. I did end for real that time.
This is incredibly insightful, and I do have a couple of questions for you while we have you here. I think the first two questions I have here, you've already mentioned them in the presentation, but if you could elaborate a bit more, that'd be really appreciated. So the first question is, can you explain a bit more how the array of radio pulsars is distributed across the galaxy to contribute to detecting low-frequency gravitational waves? I think there is a picture in between, right? Yeah, if you could
absolutely
explain a bit more.
Yeah, and so this, the array has been built over time by drawing upon the hard work of many people and many, many hours with lots of different radio telescopes conducting surveys across the plane of the Milky Way and out of the plane of the Milky Way. And so there are only about 3,000 known pulsars in the galaxy right now. We know that the galaxy has many, many more pulsars than that, but we only know where 3,000 of them are. So they're really, really rare, kind of precious objects to all of us. And from that, here are 68 of them. So we've taken the best of the best pulsars. And the reason why they're distributed the way they are has to deal with how those surveys were conducted, which telescopes conducted those surveys, how sensitive were those surveys. And so it just turns out that certain directions of the sky have been mapped with more sensitivity than other directions of the sky. That means that we can go out farther into the galaxy to find more pulsars. We happen to be kind of right in the center of this ugly mess right here. But you can see that in certain directions versus other directions, we can see more pulsars or fewer pulsars. And so we are continuing to conduct surveys because we haven't found anywhere close to all of the good pulsars that exist out there. And as we conduct those surveys, as new instrumentation comes online to conduct those surveys, we become more sensitive. We can make our array larger, go farther in the galaxy, and just get more pulsars. And the more pulsars we have, the more correlations we can perform. Hopefully that answers the question.
Yeah, I think it does help clear up the confusion. The second question is, yeah, I think this one you've also mentioned it in the presentation, but a bit more elaboration would be really awesome. So could you elaborate on the model used to analyze the times of arrival of pulsars and how it accounts for various other factors like random noise, etc.?
Yeah, that's a great question. And that's actually gets at the heart of a lot of the research that I've specifically done over my time here. I'm going to actually go back one slide just to simplify it for a moment. So pulsar timing has been used for many decades. And really in these kinds of experiments, we're pushing the very fundamental limits of how well we can do with pulsar timing, how both accurate and precise we can get with our measurements. And we can do very, very well, and we always want to be doing better. But the models have been, the base models have been developed for many decades. And so we understand how we can describe when pulses arrive due to the spin of the neutron star, how it's spinning, how it's slowing down, where the telescope is in the solar system. That's very well understood at this point in time. Turns out even a few years ago, it was not as well understood as we needed it to be. We needed to be more accurate than it was known, and so we work very hard to with collaborators to make that happen. We have to take into account, like I said, the motions of the pulsars, the binary orbits of the pulsars around some companion. Like I said, most of these objects are in binary orbits, and there are a lot of effects that go into play. Describing an orbit in a Keplerian fashion. So as Kepler described, it takes 5 parameters to describe how elliptical it is, how it's oriented with respect to you. But general relativity rears its head again, and these are often show very complicated higher order effects beyond Keplerian effects that are due to general relativity. And so we have to model all of those very strange, peculiar things. There's a lot of really cool science that comes out of that as well, but we have to include those in our model and then say, if we include this component in our model, how does that change? Does it match, for example, in the bottom here, does it match whether the pulses are arriving or whether they're arriving earlier than I predicted or later than I predicted, and hopefully they match as closely as we can possibly make them without the effect of gravitational waves and without the effect of noise. And so I haven't really gone into it, but pulsars themselves are not actually perfect clocks. They're really, really, really good clocks. And we have shown, part of my work and the work of many individuals in my collaboration around the world, are showing just how good they are and what are the limits to how good they are. And what we've shown as part of our announcement of evidence for gravitational waves is that we know that they are not perfect, that there are all these other sources of noise, but that those sources of noise are smaller than the gravitational wave background that we're reporting evidence for. So we understand that even though we don't understand everything, that's okay, that we are still pulling out this common signature, and really that common signature can only be due to gravitational waves and not something else. So there are lots of other noise effects. The neutron stars themselves, they are filled with a superfluid, and that superfluid is what we call differentially rotating, and so it causes the star to wobble a little bit as even though it's spinning very, very rapidly it wobbles away from that perfect rotation ever so slightly. There is, for example, the interstellar medium, which causes a huge number of problems, because once the light breaks up into its different components, figuring out what happened to mitigate that effect is very complicated. And not only is it complicated, you don't have to do it once, you actually have to do it over time, because the interstellar medium is changing, our position in the galaxy is changing, the pulsar's position in the galaxy is changing, and so what's between us is constantly changing. And we are probing a regime of understanding the interstellar medium that's much smaller in scale than we can observe with like taking a picture of the interstellar medium in the galaxy. So we can't just take a picture and say, okay, this is what the interstellar medium is doing. We're actually probing all of these smaller scale structures. And so that's really interesting. And so there's a lot of cool science, again, that part of which I work on there, but it also makes it a really tough problem to separate the timing, the baseline timing from the noise part from the gravitational waves. But we still nonetheless think we've done it.
Awesome. Thank you so much, Michael, for the further explanation. I can see from the live audience, we have Ezequiel here, PhD students at the Argentinian Institute of Radio Astronomy. He has a question that's kind of related to the question I just raised. So he's wondering, how do you make sure you don't absorb gravitational waves in the noise model? Because I understand we need to subtract the red noise model from the residues before looking for gravitational waves. And how do you confirm the detection of gravitational waves in the residues?
Right. So I lied a little bit in my talk, and I always lie a little bit just to keep it simple, but I won't lie now. What I mentioned before was that, okay, when we look inside these residuals and we're looking for the signatures of these kind of different shapes, it's not a lie, it's partially accurate. We don't just say, here are the timing and then here's the residuals, and now let's look for these signatures. What we really do is we first fit a baseline timing model, and we say, here's a pretty good timing model. We know that because there are other effects, noise effects, gravitational waves in there, that timing model is not exactly perfect. It's what we hope, and actually what we've shown, it's pretty close, that we're in a regime such that if I can ever so slightly tweak the different parameters of the timing model. So I can say, well, the period of the pulsar is this, but is probably around this, but I can let it be tweaked ever so slightly. And then its position on the sky are these two numbers in latitude and longitude, but I can let them be tweaked ever so slightly. I can tweak all of those, and on top of that, then add in noise and parameters for the gravitational wave background. And what's been shown is, in doing that, in this what we call linearized regime, that all of our pulsars are in this regime where you're close enough to the correct timing model that now when you add in those extra parameters, you're not deviating away such that all of our assumptions are invalid. So all of the assumptions we have in the timing are valid, but now we can include these random walk type effects in our or other signatures of gravitational waves or noise, and then that's perfectly valid. And so it means that we're able to do this simultaneous fit, everything all together. Once we have our initial timing model for this pulsar and this pulsar and this pulsar and 68 pulsars, then we can perturb it ever so slightly, and that's how we really begin our gravitational wave searches.
Got it. Very cool. Thank you, Michael. And the last question is from myself. I'm wondering, in your opinion, what are the biggest challenges for us to search for individual supermassive black hole binary system moving forward?
That's a great question, and I was at a session just a couple years ago, right before COVID, a panel at the American Astronomical Society meeting, and it was very interesting because we brought together people working on the gravitational wave side and people working on the electromagnetic side. And what was the interesting part of it was different people had different opinions about who would find evidence for an individual source first. And it wasn't exactly what you would expect. It wasn't like, oh, we are going to do it first. Or some people said, oh, you're going to do it first. Or these people are going to do it first. And so what we believe is that in this decade, so in the coming years, we will be able to observe several gravitational, or several, I should say, supermassive black hole binary sources, individual ones. That will probably be a combination of some part of that comes from electromagnetic observation. So for example, on the center right here, you see the brightness of a quasar over time, and it's following this sort of periodic model. That gives us kind of a clue as to where we might target to look for continuous waves from gravitational wave sources. On the flip side, if gravitational waves say let's say we find a continuous wave source, we can say, well, it's over there. Now let's go match with electromagnetic observations and try to build that picture. And really only when we have both electromagnetic and gravitational wave are we going to get a complete picture. That's true of, as I mentioned before, everything in the universe.
Got it. Thank you, Michael, for elaborating more on that. I think we're coming up closer to time here. So
Sure.
Once again, a huge thank you to you, Michael, for joining us today and presenting this incredibly insightful workshop. It's really inspiring. And before we wrap up, I want to say again that here at Dora Hacks, we love to support innovation in frontier tech, and we help fund innovators, research ideas and projects via hackathons, grants, bounties, etc. So if you're doing research or developing projects in areas such as astronomy, space tech, quantum, etc., feel free to reach out to us. You can check out our website at dorahacks.io, where you can find plenty of ongoing grant and hackathon programs. You can also send us your proposal directly, then our team can review it and potentially fund your project. And if you don't want to miss out on the upcoming workshops we are about to host, make sure to follow us on YouTube and Twitter at Dora Hacks. With that being said, I want to say thank you to you, Michael, one more time for taking the time to be here with us today, especially to kick off our first workshop episode on astronomy. We really appreciate it. And moving forward, we are committed to continuing our workshop series on astronomy. And lastly, thank you to all the audience for joining today. And that concludes this episode of Dora Dōjō Workshop. Thanks, everyone. We will see you soon. Have a good one. Bye-bye.
Thank you very much.